Hi friends, welcome to the lecture of linear algebra. In last lecture, we have seen what is a analytic polynomial for a linear operator and analytic polynomial for a corresponding matrix, and monic polynomial and same for minimal polynomial. First, we have seen what is a minimal polynomial for linear operator T, and after that, we have seen what is a minimal polynomial of a matrix A. Now we have to see some theorems depending on definition of minimal polynomial and analytic polynomial. Okay. First one is the minimal polynomial of a matrix is a divisor of divisor of every polynomial that annihilates the matrix A. Sorry, or any matrix. Okay, now we have to prove if this if m of x is any minimal polynomial of a matrix and f of x be any analytic polynomial, then we have to prove that this m of x divides f of x. That is, if we have given one matrix, then the minimal polynomial of a matrix A is a divisor of every polynomial that annihilates the matrix A. And in last lecture, we have seen what is a analytic polynomial. If T be a linear operator on a n-dimensional vector space V over the field F, and f of x is any polynomial over T, then a polynomial then if f of t equal to 0, then we say that the corresponding polynomial f of x annihilates the matrix A or the operator T. Same for operator and matrix A. Okay. Now we have to prove this theorem. Let m of x or mx be a minimal polynomial for matrix A, or we can say that it is for linear operator T, and f of x is any polynomial which annihilates the matrix A. As here given that f of x is an analytic polynomial, it means that f of a is equal to 0, and we know that minimal polynomial is a smallest degree analytic polynomial of a matrix A. It implies m of a is also 0, which implies m of a equal to 0 and f of a equal to 0, which implies, or it is, that is nothing but. Okay. Now, as here f of x and m of x, or fx and mx are two polynomials, then by division algorithm, there exist polynomials q of x and rx such that this f of x is nothing but m of x into q of x plus r of x. Okay. As fx and mx be any two polynomials, then by division algorithm this f can be written as a m of x into q of x plus r of x, where either polynomial Rx is a zero polynomial or degree of Rx is less than the degree of minimal polynomial. Okay, let us take this one as equation 1. Now put x equal to a in equation 1. Put x equal to a in equation 1. We get f of a equal to ma into q of a plus r. Okay. Now we know that f is a analytic polynomial. It means that f of a will be equal to 0, and m is nothing but the minimal polynomial. Therefore, it is also 0 into q of a plus r. From this we can write r of a is equal to 0, as R of matrix A will be equal to 0, then by definition of analytic polynomial of a matrix A, this R of x is an analytic polynomial for matrix A, since R of x annihilates the matrix A. Therefore, polynomial Rx is the analytic polynomial for matrix A, which implies Rx is analytic polynomial of matrix A, or for matrix A. Okay. Now there are two possibilities for polynomial Rx, whether either Rx is a zero polynomial or it is a non-zero polynomial. If possible, suppose that Rx is a non-zero polynomial. Let, or if Rx is a non-zero polynomial, non-zero polynomial. Here, Rx is a non-zero polynomial and Rx annihilates matrix A, and Rx annihilates A, and degree of Rx is degree of polynomial Rx is less than the degree of minimal polynomial. Okay. So but here we have taken m of x as a minimal polynomial, but here we get one polynomial Rx which has a degree less than the degree of minimal polynomial and which annihilates the matrix A, which is contradiction to our definition of minimal polynomial, since here given that mx is the minimal polynomial. As mx is the minimal polynomial, then it is the lowest degree polynomial which annihilates the matrix A. But here we get one polynomial Rx which has a degree less than mx and which annihilates the matrix A. This is not possible, and this contradiction arises due to our wrong assumption. That is, Rx is a non-zero polynomial. Hence, Rx must be a zero polynomial. Okay. So it contradicts to mx as a minimal polynomial, and hence Rx must be a zero polynomial. As Rx is a zero polynomial, that is Rx is equal to 0. Now we have to take this Rx equal to 0 in equation 1. Then we get from 1 f of x is nothing but mx into qx, since R of x is a 0. Now we know that the definition of divisibility. Let us take the divisibility of two integers. If a and b are two integers, then b is said to be a divisor of a if there exists an integer q such that a equal to bq. So here there exists a polynomial q of x such that f of x is nothing but mx into q of x. Then by definition of divisibility, this m of x divides f of x, which implies m of x or minimal polynomial divides fx. But here fx is the minimal polynomial and fx is the any analytic polynomial. Therefore, from this we conclude that a minimal polynomial, as here we have taken fx is any arbitrary polynomial which annihilates the matrix A, and a minimal polynomial divides the analytic polynomial. Therefore, from this we conclude that a minimal polynomial is a divisor of every polynomial that annihilates the matrix A, and that is we have to change the. Okay. Now the next one is let T be a linear operator on an n-dimensional vector space. Vector space V over here. F. Let f of x is any polynomial over f, and if p of alpha equal to c into alpha whenever alpha is not equal to 0 and c belonging to field F. Then we have to prove that f of p of alpha is nothing but fc or. So, if P be any linear operator on an n-dimensional vector space V over the field, and Fx is any polynomial over the field F, and if T of alpha is nothing but C into alpha for each alpha is not equal to 0 and C belonging to field F, then we have to prove that F of T of alpha is nothing but F into F of alpha. Okay? Prove. Given that T be a linear operator on V over F, where V is a n-dimensional vector space. Okay, and suppose T of alpha is equal to C into alpha, where alpha is not equal to 0 and C belonging to F. Then by definition of characteristic value, C is said to be a characteristic value of a linear operator P if there exists an alpha which is not equal to 0 such that T of alpha is equal to C alpha. Therefore, from this definition, this C is nothing but the characteristic value, which implies C is characteristic value of linear operator T. Now, as given that f of x is any polynomial over the field F and dimension of the vector space is n, then this polynomial fx can be expressed as a0 plus a1x plus a2x square plus up to so on an x raised to n. From this, f of t is nothing but a0 I plus a1t plus a2t square plus up to so on an t raised to n. Now take f of t of alpha, that is consider this one. Consider ft of alpha which is equal to a0 I plus a1t plus a2t square plus up to so on an t raised to n of alpha, and we know that which is nothing, I is a linear operator, so which is nothing but a0 into I of alpha plus a1 into t of alpha plus a2 into square of alpha plus up to so on an into t to the power n of alpha. Now, which is nothing but a0 into, let us take I of, as this one is the identity operator, then image of alpha is alpha itself. Okay. Now, T of alpha is equal to, we know that T of alpha is nothing but C alpha. It is a given C into alpha. Now T square of alpha is nothing but T into T of alpha, and T of alpha is nothing but C into alpha, and T is a linear operator, then it is nothing but C into T of alpha. Again T of alpha is nothing but C alpha, which is nothing but C into C alpha, and which is equal to C square alpha. Similarly, we can prove that T cube of alpha is nothing but T into T square of alpha, and T square of alpha is C square of alpha, and C square is, as T is a linear operator, then which is nothing but C square into T of alpha, and which is equal to C cube alpha, C cube into alpha. Okay. Now up to so on, T to the power n of alpha is equal to C raised to n into alpha. Now we have to put these values in this equation. Then we get Ft of alpha is nothing but equal to A naught I of alpha is as it is, A naught I of alpha plus, now A1 T of alpha is nothing but C into alpha, A naught C alpha plus A1 T square alpha is C square alpha plus up to so on An C raised to n into alpha, which is nothing but A naught I plus A1 C plus A2 C square plus up to so on An C raised to n of alpha. Now, by definition, this A naught I plus A1 C plus A2 C square plus up to so on An C raised to n is nothing but f of C, as f of x is a polynomial of degree n. So, which is nothing but f of C of alpha, and that is we have to prove. We have to prove f of t of alpha is nothing but fc of alpha, and hence the proof. Okay. Now, there is one important theorem on characteristic polynomial, valid Hamilton's theorem. Okay, let T be a linear operator on an n-dimensional vector space. V over the field F. Then if fx is characteristic polynomial of T, then T satisfies its characteristic equation. Its characteristic equation. That means if fx is a characteristic polynomial for linear operator T, then f of T equal to 0. Or statement, every square matrix satisfies its characteristic equation. Okay, now we have to prove this theorem. Okay. Now, given that T be a linear operator on an n-dimensional vector space V over F, let V be an order the basis for vector space V, and A be the matrix of T, matrix of linear operator T with ordered basis B. Ordered basis B. Okay. Now that is, this is nothing but A be the matrix of linear operator T with ordered basis B. Now we know that a characteristic polynomial for T and the characteristic polynomial for matrix A is same. Okay. Now since A is the matrix of T with respect to ordered basis B, so matrix A or the minimal polynomial, characteristic polynomial, determinant, trace, all those things of matrix A are similar or equal to the characteristic polynomial, minimal polynomial, trace, determinant of linear operator T. Therefore, actually we know that characteristic polynomial of a linear operator T is nothing but the characteristic polynomial of a matrix A. As T is an n-dimensional vector space over the field of, then A is a square matrix of order n. Let A be a square matrix of order n. That is, it is an n cross n matrix, and we know that the characteristic polynomial of matrix A is nothing but the determinant of matrix xi minus A. So now consider determinant of xi minus A is nothing but xi minus A is equal. Just take this as a on this side. So determinant of xi minus A is nothing but x minus a11 minus of a12 minus of a13 up to so on minus of a1n. It is a square matrix of order n cross n, which is nothing but minus of a21 x minus a22 minus of a23 up to so on a2n and so on. Minus of an1 minus of an2 minus of an3 minus of an3 and so on minus of ann, x minus ann. Let's write this one as once again, minus of an1 minus of an2 minus of an3 up to so on x minus an. Okay, now each element of the matrix here, each element of the matrix xi minus a is the polynomial in years of degree at most 1. Okay, here there are some elements which are in terms of polynomial and remaining may be polynomial, or they are the constant terms, then its degree is either 1 or 0. Okay, now which implies each element of the matrix adjoint of xi minus a is a polynomial in years of degree n minus 1 or less than n minus 1. Now how it is? Since each entry or since each element of matrix adjoint of xi minus a is the cofactor of the elements of matrix xi minus a, as each element of the matrix determinant of xi minus a or the matrix xi minus a is the polynomial in years of degree at most 1. Okay, so each element of the matrix adjoint of xi minus a is a polynomial in years of degree n minus 1 or less than 1, since each element of the adjoint of matrix adjoint of xi minus a is the cofactor of the elements of the matrix xi minus a. And how will you find out the cofactors? If suppose we have to find out the cofactor of the element a1, that is term a11, which is x minus a1, then we have to take this, and in this way we find out the cofactor of the element a11. And here there is possibility that the element may be a polynomial of degree n, since they are less than n minus 1 or equal to n minus 1, and here there is a possibility of getting one element which has a degree n minus 1, since here there is one term x which is not in this cofactor term. So each element of the matrix adjoint of x minus a is an polynomial in x of degree n minus 1 or less than n minus 1. Okay, now the matrix adjoint of xi minus a can be expressed in matrix polynomial as follows. First we have to see we see for a 2 cross 2 matrix, and we generalize it is for a n cross n matrix. For example, here take A be a 2 cross 2 matrix. Okay, as A is 2 cross 2 matrix, then A minus xi or xi minus a is nothing but A minus xi is A11, A12, A21, A22, A11 minus x, A12, A21 and A22 minus x. This is the A minus xi. Now we have to take determinant of A minus xi. If we take determinant of